one another. All right. Next, we're going to move on to some calculus of vector-valued functions. And the first thing that I'm going to show you is a couple of definitions. So our first definition, what does it mean to take the limit of a vector-valued function? So the limit as t approaches some value a of our vector-valued function r of t is defined to be the limit of each of the component functions. So I take the limit as t approaches a for the first component function. I take the limit as t approaches a for the second component function. And I take the limit as t approaches a for the third component function. This is sort of a technical definition that should be obvious. So, for example, if I have some vector-valued function r of t, which is equal to maybe 3t comma t squared comma e to the t, and I want to know what's the limit as t approaches 0 for my vector-valued function r of t. That's going to be the limit of each of these components individually. Oh, this is maybe sort of a boring example, because as t goes to 0, 3t will also go to 0. As t goes to 0, t squared goes to 0. And as t goes to 0, e to the t becomes 1. So in this case, the limit is defined for each of the component functions, so the limit is defined for this vector-valued function as well. Why do we want this definition? Well, it's to get onto more interesting definition, and as you may recall, the definition of derivative relies on limits. So when we define derivatives for our vector-valued function, we're going to say the derivative of a vector-valued function r of t. We usually write, if you want to use Newtonian notation, r prime of t, which is also using Leibniz notation, the derivative of r with respect, the derivative of r of t with respect to t is, thankfully, what we want it to be. It's the derivative of each of the component functions. But we could define this in terms of limits. It's the limit as h approaches 0 of r of t plus h minus r of t all over h. This is exactly our functional definition of derivative when we were dealing with real valued functions, boring two-dimensional functions. Now that we're talking about vector-valued functions, this definition is the same. The thing that I want to point out is that functionally, this is going to be exactly equal to the derivative of each of the component functions. So I might write that as x prime of t comma y prime of t comma z prime of t. So an example would be